So I will run this first block. You can click this button to run, and if you see a ampersand like start like that, it means that it's running. And then when it turns into a number, it means that it runs successfully. So I will also import some external module to our notebook. So first module, the Solaris, is quite important. Let's see the GitHub page of it. This is developed by Cosmic, which is actually the same organizer who actually initiated everything the SpaceNet has, and they kind of work on that. They hosted the challenge of the SpaceNet. So this is a really good platform to make you process the SpaceNet image, since our data are really similar to SpaceNet's architecture, so we can kind of use this. Right, so this is their page. If you have something you want to look into details, you can always go to their official web page to see how to use their APIs, how to use their library. So we will use a lot in this tutorial. You will see later. So basically we call it a short name called SOL. So the Solaris actually helps us to process the image, load them into some PyTorch neural networks, and then do inference. For example, you want to do inference or prediction on a small patch of the image, and then stitch them together. So Solaris has their own package to do that for you, which is really handy. That's how we make this notebook so short. Otherwise, we have to write everything into a separate function or class. But thanks to Solaris, we can just write everything down in a single line. You will see soon. So the third one is very simple, just some plotting preference. Keep it as it is. So this is the first place where we are going to touch the data. The first data set we use in this data books are the data buildings. We can actually click into the file browser to see. So we have two folders here, RGB plus LF, and the GeoJSON buildings. They're combined from two datasets, like I mentioned before, the SpaceNet satellite images and the USGS 3D EP LiDAR. So the first one in here is buildings, and the buildings are 200 by 200 meter satellite images. All right, all these data in this folder are from the second area of interest, the Las Vegas area. So you will see next here, so these buildings are from Las Vegas. We merged the LiDAR and the RGB image into 4-channel image. Notice that this time it's 4-channel, not a 3-channel RGB. It's RGB plus elevation attribute. So that's why we call it RGB. All right, run this block to define all the folders. So we have data dir, image dir, and building dir. So building dir is the GeoJSON buildings. In the first one, the image dir, the RGB plus LF, it may be a little bit laggy because we have thousands of files there. If we drag here, you can see that the extension of these files are TIFF. These are GeoTIFF files. They contain not only the image information, but also some metadata such as the coordinates of the bounding box of these tiles. And then we have GeoJSON buildings. These folders are considered to be the labels of the images. So JSON file, usually you can even just open it and look at the content of this. This is basically some coordinates of a polygon or several polygons of the building. It describes the extent of a building. So basically in this building detection task, we want to make our model to predict the buildings in the images as close as possible. All right, just go back to make this faster. All right, here we show an image example, the image 1423. This is called the chip ID. If you run it, so they will the code will actually run something. First part is the reading this 4-channel image from GeoTIFF. This is a file name, and then we use SK image to load the image, and then the first 3 channels are RGB. This is easy to understand because we have merged the RGB 3-channel image into a 4-channel, and the last one is the elevation attribute. here we plot them separately in two images. So the left one is the satellite image with colors. You can see roofs, roads, trees, and pools. And the second image is a single channel one. That's why we plot it in a grayscale image. You can notice that we can easily tell from an image that these lighter parts are either the house rooftop or the trees because they have higher elevation. But instead from here, we have to look in from the color information here. In the second image, we can see directly where the elevations are higher, and that's really helpful to tell the buildings from an image, right? And the third part, we're reading the GeoJSON file and convert the polygons to mask. This is quite important because neural networks are more easily understanding the mask information. So the neural network will try to predict things, every pixel within an extent of the building. It is able to tell whether a point is falling into a building or not, but it's not very accurate at telling the boundary of the building. This is very tricky. So you can looking for more details. I'm also willing to tell you more details after the tutorial or at the break session. So basically, in order to train it or to visualize it, we convert the building polygons here according to the reference image, which is the original image, to a mask. And the third image shows what the mask looks like. That makes sense, right? So we call it footprint because all these dark blue colors represent the ground truth is. So our network has to predict exactly what this image looks like. So here you can see that we're using the SolRS package to do that. Instead of writing your own, you can simply call it with one line, and then it will help you to convert the polygons into mask. Very handy. All this fourth parts are just trying to display the satellite image and building footprints for you. These are just visualizations. Right. And this part, in this function, we're trying to convert every single polygons into mask because later we may want to do some more predictions. To do them in a batch, we can simply put them in a loop. So here you can see that for everything in this image file list, do the vector mask footprint mask conversion. Just run it. So it will take a while. So in the meantime, we can go down here to see we can start inference on sample data. That's we skip the training because that will take a long time and then a lot of training resources. In this light version notebook, and we have already downloaded the model weights, and I will show you soon in the following parts of how to load it and how to do prediction. So we have a fancy name for prediction in neural networks. It's called inference. We're going to input the image into the model and let the model infer the target or the answer of the problem we want. For example, in this case, we want the model to predict the building footprints for us. And for this notebook, all training setups are saved in this YAML format, YML format. In this folder, let's open it. It's configs, buildings. And then you can see that we have 3 different configs. The first one is RGB only, which tells the network to only use the RGB images as input. That means that we have 3 channels, the red, green, and blue. And the second configuration use only the elevation. It tells the network only to use lighter elevation images input, and it will be a single channel network input. And the third one, which is my favorite, and it's going to be the most accurate model, is the RGB plus elevation. It uses both RGB and the lighter elevation as merged input. So it's 4 channel. So with the original SpaceNet context, you can imagine that they are by default the RGB only. In this work, we actually introduce an additional channel, the elevation, to help. So you will see that if you only use elevation, it will be not as good as RGB because definitely it contains only 1/3 of information, but in a different format. But then if we put all of them together with a 4 channel, we have a better chance to achieve higher score. So this is the SolarRes function to load that config files. This is the path we have. We run it, and at the same time, I will open this file. YAML file is simply a text file. Put it aside. So you will see that we define some information, and then maybe these keys are very ciphering for you. They're just enigmas, but don't worry. If you want to know more details, go back to the SolarRes page here. All right, here it is. So in this page, it tells you all the information of the YAML file. It will change a lot of settings in the network, so it's quite important. But in this tutorial, you can just keep it as it is, like this. Some information here is, first of all, we are going to use a model called XDXD SpaceNet4. What does it mean? It means that we use the model from SpaceNet Challenge 4, and it was developed by the XDXD, who was the winner of that contest. And then a few infos here. You can see that we set the chain to true and infer to true, pre-chain to false. This is actually misleading because we are indeed using a pre-chain model. The reason why we set to false here is that we do not want to use the pre-chained model from XDXD, who submitted the model with only 3 channel input, because remember that in SpaceNet contest, they only use RGB only image. So here, we're using a custom model dictionary here to load the model. Don't worry about that. Just browse through these YAML config and think of all these titles. What does it mean? So we will touch them later in the notebook, and I will just keep it here for reference. All right. So this is our next. Cell. Like you see that we start to load a custom multi-channel input VGG16 UNet model, and let's take a look at what this network looks like actually. So it is essentially just a Python code here. Like I said, originally developed by XDXD in SpaceNet 4 challenge, and then we had a header here to trying to modify the input channel of the original neural network, so we allow multiple different settings. For example, you can say channel equals to 1. That means that we are only going to take one channel input, such as the elevation only. And here the customer model set, we take in channels the config this number. Let's find this number here. It will be this number, so 4. Because we are in the RGB plus elevation YAML file, it will be 4 channel. So these means that we will going to create a custom model with 4 channel input, and then the architecture of it will be VGG16 UNet. And then dictionary or config of this custom model will be like this. So one more config here. It's called the chaining model destination path, which is right here. And see if we can find it. It is models, buildings, RGB plus elevation. See, remember that we downloaded this model file from the S3 downloading script. So this is already here. And then we set chain to false because we do not want to alter the parameter of the neural network in the chaining, because we here only want to do the inference or prediction. And then here is some modification to reduce the RAM cost, because this time we're going to use a small free tier machine. So everything is running on CPU, and this machine has a very limited CPU memory, so we do not want to make it overloaded. So the batch size is set to only 1. So it means that it's only going to process 1 image per time. And then you will see an inferer here. We create an inferer using SolarRes inferer class. Here we're just feeding 2 important parameters. The first one is the config file, which contains every information here, and then some alteration, for example, we did here. And then the custom model dict, which is this one, we specify what model and then which model weights we need to use. So this is basically how we construct neural network information to feed into the SolarWiz class, and then SolarWiz will take care of loading and then set up the model for us. Don't worry about the details. If you're familiar with PyTorch, I actually encourage you to look into SolarWiz source code to see how exactly it is doing all these background works. And then we specify a pandas or PD data frame here. Pandas is a really famous Python library for data scientists, so you must have heard this name if you ever look into Python data science. So we start with only one simple entry. The key is image and is pointing to the image path where we specify in the beginning here. This is our example image. It's going to be like this. So the first two image, remember the first two will be our input, the satellite and the LiDAR, not this one. The footprint mask are the ground truth we used in the chaining. So this time we want to let the network figure out the ground truth itself, and then we compare to the ground truth to see how well the model is working. And then we just call it with one single line here, infer sample df, and see if it works. Wait for it. So if you have a GPU machine or GPU enabled instance, this will be much faster. Since we're running on CPU this time, it will be affected by many factors. All right, now it's done. And then let's see the result of it. It is going to go to the config inference output here, which is output view here. This is the, let's go actually go to that. You can see now that we have another directory here called results, buildings, RGB plus LF, prediction mask. And voila, this is the prediction of the neural network. So the prediction of the neural network is going to be like this. And if we compare to the ground truth using our eyes, it's really, really close, right? We have buildings, and there might be some imperfections such as the edge of the building, and then how we handle the these small inlets, right? These are details. So we need to have a quantitative way to compare the results of prediction and the ground truth. So that way we can actually say how well different models are compared to each other. So the results look good. You can see right here. Other than the visual comparison, the quantitative metric can help us better understand the model's performance. So in SpaceNet Building Instruction Challenge, they evaluate the model by F1 scores for IOU larger than or equal to 50%. You can actually search for what these means. So essentially, in a simple word, this means that they will try to measure if a building is first of all detected correctly. If you have areas overlap are larger than 50% of the original building area, that means that we have correctly detected one building. This will be our true positive. And an F1 score is basically trying to measure important information of precision and recall. It will combine information from both true positive, true negative, and false positive, false negative. That is kind of a more comprehensive score to understand the performance of a segmentation text like this. And then again, they provide their own API for measuring this. For example, here, this will convert your prediction mask like this back to a polygon style in the GeoJSON. But after running this, you are going to see a new folder here, which is called proposal GeoJSON. That is directly compared to the ground truth GeoJSON by this line here, the evaluator. We will try to evaluate the results of the prediction or proposed GeoJSON against the ground truth building GeoJSON to see what it is. And then evaluator will give us eventually this table here. We have a table of precision, recall, and the F1 score. The higher the better. And we can even see some detail here. So here we said 26 buildings are detected as true positive, and we have 4 false positive. That means that we detected 4 fake buildings which shouldn't be there. And then we have a false negative. That means that we missed 5 buildings that should have been detected. All right, let's actually run this to see if we can get it. It is quite fast, right? Same conclusion here. So at this point, actually we can go back, and before we do that, we can save the results by here, copy and then paste the results here, because we are going to compare to the results later with the new model. Just click here, copy and paste, and we actually duplicate these 2 cells down here. All right, so we can actually go back to this cell to change the config file to another one. For example, I'm going to change it to the elevation only. You know what? Let's put it by the side here, and if we compare to the original one, the channel's number now is only 1. That means that we're only going to use 1 channel as the network input. So why don't we change it here and run this again. And now done. So we can expand this and then run this one. So remember that the second image here, the next one is the original output of RGB plus elevation we had run in previous round, and this is the new round. We can compare them directly to see the results. So know that these results on the top is predicted from only the LiDAR elevation. And the bottom left one here is predicted by using both satellite image and the LiDAR elevation. So we can kind of feel that this is a little bit more accurate than this, but we don't have a quantitative comparison, right? And that's why we need a quantitative score at the end. And again, we can run the scoring cells again to compare. The top one is the elevation, and the second one here is the RGB plus elevation. You can see that in this example here, my distinction was wrong. We had 29 true positive now from using only elevation. The RGB is even a little bit distracted. So that's an interesting conclusion here. We have a much higher F1 score for this example using only elevation. So feel free to explore of using only RGB, see if you can still get similar scores, or you can even compare 3 images like this. But do know that we're not comparing the score with only one example. So a lot of times we want to use quite a few examples and measure the average of all these examples' performance, because sometimes a model can work well with this situation, but in another challenging situation, it may fail. So just bear this in mind. This is only one example. So to explore more example, we have the last section here. You can infer on random image. So in this section, we visually check some results, and the next cell here will randomly sample from the result list and rerun as many times as you wish to see different figures. Let's actually do this. So get a list of available images, and you see this line here is going to randomly choose an image file from the file list, and then we'll do very similar results like we did in the previous cells. And then here in the notebook, by default, you should all see an example from image 5510. This is the prediction, and this is the ground truth. Very challenging, right? Sometimes you rarely see buildings like this, but it's still able to detect all of this, and especially those small ones here. But those even smaller ones are quite challenging. You can see that it's missed because it's kind of covered by the chi, and I barely see anything in the elevation. So without further ado, let's actually run it. I was talking before running because once we start running, you cannot see the image anymore. Let's just wait for the results. Alright, so this is another interesting result, the 1442 image. You can see that there is a big pool or some kind of park by the side of a building or apartment condo here. You can see a lot of buildings, and these are all aligned correctly compared to the ground truth. We may miss some details, for example, the small corners. They become a little bit smooth, and in fact these small things will affect your scores quite a bit if we're measuring this in a more segmentation way of magic. For example, you want to measure pixel-wise F1 score, but do bear in mind that our F1 score introduced here in this tutorial was based on the IOU detection. So as long as you overlap 50% of the area of the ground truth, this is considered a correct one. We do not measure pixel-wise because that will be too challenging. So feel free to run this cell as many times you want. You will pop up. You will definitely see different results than me. And feel free to run this many times as you wish to see different results. And then this concludes our introduction to the first notebook, the building footprint light version. Right, after looking at the light version, we can check the full version of the building footprint notebook. This is also available in the GitHub here, so don't worry about it. Basically, this full version has something more. They are all relying on very powerful GPU resources. And note that here we said this notebook was created and tested on an MLP3 8 times large notebook instance. P3 means that we have P3 8 times large means that we have 4 times V100 GPU available on this instance. It allows us to train a lot of large-scale network with quite a few amount of training data. For example, this case is a very good example of doing this. These training will not be possible on the small T3 median before, and then because we either do not have a nice GPU to run, or we do not have enough RAM to hold all the model information we need to optimize there. So in this training session, I'm going to just show you what is more than the original light version. Basically, so it takes the SpaceNet context provides 2 groups of the data. The training directory contains data to train models and then test public for you to score, and then this submission will be then ranked by the competition organizers to see which one team is the best one. However, since we do not have the tested public labels available, so we are only going to split 30% of the data from the training to pretend that it's actually the test data. We call them the train data and then blind test data. We're only going to use 70% of the data for training. So this is the exact line here. We're going to select only 70% or 0.7 of the total training image as training, and then the other 30% are going to be reserved as holdout data. We call this in machine learning area. So see that we have 3,084 images total, and we use this number of images for training, and then the rest of the 897 for test. And as you remember that in the light version, it will take a long time to run all these 800 tests. So we did not do that in there, but with a GPU, and then especially the GPU, the powerful GPU you have in pre-free 8 times large AWS instance, you will be able to run this in a quite fast way. The rest of them are quite similar. You see that we have a trainer here. The trainer also takes almost the same input as the inferer. However, notice one difference here. We have none as the weight path. The reason that we want to train from scratch. With the clean model, we do not want to load any pre-trained model, but you can also do this to try if it helps or if it didn't work. So inference is the same as the light version, but at the end, we also have a section to batch inference and scoring on all test data. Here we have test DF, which was including all of that 897 images. We do inference here. So see that with the help of GPU, you will be able to run this with only 3 minutes. Just imagine that with a CPU, how much times you are going to spend just to wait for the inference to be done. And then remember, this is only inference. The training is going to be only worse. And then these are the batch scoring. If you remember that, we can use some score function to trying to calculate the true positive, false positive, vice versa. And this is basically doing the same thing. These cells are going to be output these information here, and you can see it's printed out here. So we can see that the RGB plus elevation model gives a precision of 0.87-ish. Recall of this, and then the F1 score of this. So not bad at all. And for reference, we put a score of winners in the original contest, especially for the Las Vegas data from the original contest here. And you can open this page to see it. And this is the post describing the eventual result. We use the score of Las Vegas for reference. But that means that this is already comparable to the first place or second place, but do keep in mind that we are not using the actual test data because we do not have the actual ground truth label to measure how well we did. So we are not using the same test data, but the idea is similar. And then the rest of the notebook are also similar. This is how to reproduce the paper figures. But that's all about the full notebook. If you're interested in reproducing the training and the batch inference scoring, you can definitely try to get yourself a GPU enabled machine, for example the AWS instance or something else you have in your local or on-demand machines. But this will be quite interesting to see if you can even do something better than us. But that concludes the introduction of the building footprints, and next we will move to the road network, which is a more exciting topic to have. Just a quick summary of what we have been seeing in the building detection notebooks. We have 3,084 merge tiles in total, and we split them by 70% and 30% to chain and testing. So the model we used is UNet with VGG16 backbone. You can search for the details of these architecture. Eventually we'll want to output the building footprints label. It took 1.5 hours to chain for 100 epochs on P3 8 times large instance. So we didn't reproduce this training process in the tutorial because of the limitation of time and resources. But if you have these two in your hand, you can definitely try to reproduce the training and see if you can still get the same performance. I believe you will. And here's some examples you've seen in the full notebook. This is also appearing in the paper. So to compare the results, we compare with the previous contest, and then notice that we scored using different test sets. So this is not an apple-to-apple comparison. This is just for your reference. And the section takeaway is that compared to using RGB only, as in the original SpaceNet competition, the model chain using only LiDAR elevation images can achieve score only a only a few percent worse. When combining both RGB and LiDAR elevation in training, the model outperforms RGB only model. LiDAR data could be as useful as RGB satellite images in building detection application. That means if you have data from 2 different sources, you can try both of them, or you can combine both of them to see if it improves your performance. And in many use case scenarios, LiDAR data can be more flexible to acquire than satellite images. Just imagine you have some machines installed on a drone, you can do that again. But satellite image may be not that flexible to collect in some special situations.